Morning students. Today we'll be learning about DC generators. Coming to the DC generator or a generator. A generator is a device or a machine which converts mechanical energy into electrical energy. Whereas a machine which converts electrical energy into mechanical energy is called as motor. A DC generator is a machine which converts mechanical energy into electrical energy. If the electrical energy is of DC, then you'll be calling it as a DC generator. If it is AC, it is called as AC generator. The conversion is based on the principle of dynamically induced EMF and Faraday's laws of electromagnetic induction. Coming to the construction point of view, DC motor as well as DC generator have same parts. The only thing is, based on the input energy, the particular machine will be acting as a motor or generator. Coming to the schematic view of this 4-pole DC machine. Here this is the terminal block or terminal box. Here these are the commutator segments, commutator, and these are the brushes. These are the poles or pole core. This is pole shoe. These are the field windings. This is the armature. The centermost part is called the armature core. The armature core is filled with slots are filled with winding called as armature conductors or armature winding. This is called the field winding. The outermost covering of all this one is called yoke. This is called the base plate. So in detail, we'll be learning about all the parts of the DC generator or a DC machine. Coming to the yoke, the outermost frame of the particular DC machine is called as yoke. It is made of cast iron or cast steel. It provides mechanical strength as well as provides a low reluctance path. It provides low reluctance path for the flux. Next, pole core and pole shoes. Pole cores are joined to the yoke with the help of bolts or welding. The function of this pole core is to hold the field winding. On the pole core only we will be having the field winding. The field winding will be wound on the pole core. Core is nothing but a piece of iron or steel. They carry the field winding or they house the field winding, and pole shoes are fastened to it. Pole shoes are fastened is nothing but fixed to it. Pole shoes are used for supporting the field coils as well as they spread the flux uniformly in the air gap. Next, field winding. They are made up of generally enamel coated copper wires. All the wires or coils which are used in electrical machines are made up of enamel coated copper wires, and the field coils are former wound and placed on each pole and are connected in either in series or in shunt. They are wound in such a way that they are energized. They alternately form north and south poles. What do you mean by energization? The process of giving electrical energy or current through a wire is called energizing. Next, armature core. Armature core is nothing but the rotor part of the DC machine. It has armature slots. Inside these slots, we will be placing the armature windings. The armature core is made up of thin laminations in order to reduce the eddy current losses. And they are also provided with air ducts. They are nothing but air holes for the axial flow of air, which serves as cooling for the armature. See, this is the uh, view of this armature. So these are the armature slots. This is the armature. The whole thing is called the armature. These are the armature windings. The windings are placed in the slots of this armature core. They are made up of thin laminations of silicon steel material to reduce the hysteresis and eddy current losses. Armature winding, the same manner, same as that of field winding. Here also you'll be having enamel coated copper wires which are worn or which are fitted in the slots of armature. These armature windings can be worn by any of these two methods. One is lap winding, another one is wave winding. We prefer to use lap winding when we use low voltage and high currents, and we prefer when we prefer high voltages and low currents, we go for wave winding. So this is the commutator. These armature conductors are connected here to this one, which is called this commutator. What is the function of this commutator? It is generally made up of copper bars separated by a thin sheet of mica insulation. The function of this commutator is in a DC generator is to collect the current from the armature conductors, whereas in case of DC motor, it gives the current or provides the current to the armature conductors. In DC generator, it will be collecting the current from the armature conductors, whereas in DC motor, it will be providing or it will be uh, giving the current to the armature conductors. Here it will be collecting, it will be giving here. So coming to the brushes are used for uh, collecting the brush current from the commutators. They are generally made up of carbon or graphite. They rest on the commutator segment and slide on the segments when the commutator rotates, keeping the physical contact to collect the supply current. So coming to the EMF equation of a DC generator, this is the derivation. So let phi be the flux per pole in the Webers, and Z is the total number of armature conductors, and P is the total number of poles in a DC generator, and A is the number of parallel paths in the armature, N is the rotation of the armature in RPM, E is the EMF induced in the armature. Then the generated EMF EG is equal to EMF induced in any one of the parallel paths. The EMF generated in a conductor according to Faraday's laws is equal to d phi by dt volts. Therefore, how much amount of flux is being cut by the conductor in one revolution is d phi. The flux cut by the conductor in one revolution is d phi. This flux depends on the number of poles. Therefore, phi into P Webers. And the number of revolutions in 1 second is n by 60. Now, time for one revolution is 60 by n. Therefore, according to Faraday's laws of electromagnetic induction, energy generated in a conductor is equal to d phi by dt, where d phi is equal to phi p and dt is equal to 60 by n. Therefore, phi p by 60 by n, that is equal to phi pn by 60. Phi pn by 60. See, we need to consider even the total number of conductors also. Total number of conductors and the number of parallel passes. Therefore, for lap winding, the number of parallel paths is equal to P. A is equal to P. Parallel paths are represented by capital A. Therefore, the number of parallel paths in lap winding is A is equal to P. Next, the total number of total amount of EMF generated is equal to phi Zn by 60 into P by A, where A is nothing but the parallel paths. Here for lap winding, the parallel paths is A is equal to P. Therefore, here phi Zn by 60 into P by A or P by P, that is equal to phi Zn by 60 volts in case of lap winding. Whereas in case of wave winding, as we know that number of parallel paths A is equal to 2. Therefore, The EMF equation is 5Zn by 60 into P by A, where A is equal to 2 here. If you calculate this one, 5Zn by 60 by 2, that is equal to 5Zn by 6, 5Zn by 5Znp by 120 volts.